So refreshing our memory on solubility rules. There's one rule that kind of supersedes everything else, that kind of takes over everything else, and it has to do with number 1 and number 4, which is why they're kind of bolded, and it's called, and we'll just refer to it as the Big Daddy rule. All right. Basically, any ionic compound that contains an alkali metal or ammonia is going to be soluble. Also, if it contains a nitrate group, NO3, chlorate, chlorite, or is that acetic acid? Or an acetic group, they're going to be soluble. That means they're going to break down in water and form ions. So anything that has what's listed in number 1 or number 4 is Big Daddy. And big thing to know on that is always soluble. If my pen starts writing. Just set it on that desk behind you. All right. Now, the other rules, the other 2 rules that we have, and I gave you some acronyms for that, or whatever you want to call them, anagrams. I don't know the real word for it. But we said that Hal Hughes, no wait. The other one we said is Hal hugs Aggies pretty badly. Basically, anytime that we have, halogens are always soluble except, so halogens are soluble except for whenever they're combined with mercury, silver, or lead. All right, so mercury, silver, and lead are the bad guys. They are the ones that, if they're combined with a halogen, with something from column 7A, fluorine, chlorine, bromine, iodine, that's what makes them insoluble. Any other time you see something combined with a halogen, it is always soluble. All right, and then the other, I guess that would be rule 3. We said Sol can bag hags pretty badly in Shreveport in Argentina. Yeah. Well, but it has to do with rule 5. But this is, I'm giving you 3 major rules. Big Daddy is rule number 1. Yeah, I'm kind of making some general overarching rules. All right. So Sol can bag hags pretty badly in Shreveport in Argentina. Kind of, I guess, depends on how you look at that. But anyway, sulfates are soluble except when combined with calcium, barium, mercury, lead, silver, and strontium. So sulfates are soluble except when combined with these elements. Now, again, Rule number one, Big Daddy supersedes everything else. If it's a group 1 metal, and if it's a group 1 metal, always soluble. And then ammonia is always soluble. So this rule kind of controls everything else. If it's not a alkali metal involved, then you have to start looking at the two bottom ones, rules 2 and 3. And that's going to be kind of the driving factor. So we're going to look a couple of pages back. If I can find my notes on this. All right. So I think this is the one I'm looking for. All right. Yeah, it should be a couple of pages. I'm looking for number 8, actually. There it is. All right. Now, we did number 7. Oh, yeah. I skipped number 7. Sorry. I see what you're saying now. All right. So this is where we're going to start talking about net ionics. Actually, we're going to talk about a couple of things. We're going to distinguish between what's called a molecular equation. Molecular equation is what you're familiar with. That's just a normal balanced equation where we show everything as is. And then we're going to do something called a complete ionic equation and a net ionic equation. All right. What ionic equations do, if something is soluble in water, if something can make an aqueous compound, then we're going to show it as its ions. So the key thing here is in a molecular equation, we have to show state. And I'm going to say state of matter. And can anybody remind me what symbols or what notations do we use to show state of matter in a chemical equation? All right. So we have S, and S is going to tell us what? Solid. L is going to tell us what? Liquid. G is gas. And AQ is aqueous. All right. And this one is the aqueous is the one that we're looking for in these type of reactions. Aqueous tells us that it is an ionic equation or an ionic compound that's soluble. So, so the first thing we need to be able to do is look at the word equation and write this as a formula equation or molecular equation. So potassium chloride. What is potassium chloride going to be written as? KCl. All right. So that's where we're going to start. Potassium chloride, KCl, is combined with lead 2 nitrate. So that tells us that lead is a +2 charge. And if we look at nitrate on the polyatomic ion list, nitrate is a -1 charge. So that means that we're going to have PbNO3 with a 2 on the outside. Does everybody understand why I did that? All right. Now, that's all the information we have. So what do we need to do with this? Yeah, we need to finish it. So we need to figure out what's going on. This is what type of reaction? Double replacement or double displacement. So the potassium and the lead is going to switch. So we're going to have lead chloride. And that was lead 2. So how many chlorines am I going to have? 2. So it's going to be PbCl2. and then it's going to be K, and potassium is a +1, so it's just going to react with one nitrate group. All right. Now, what's the next step? What do we have to do? Balance it. All right. On this side, we have 1 chlorine. On this side, we have 2. So what do I need to put right here? 2. All right. It's not totally balanced yet. Okay, so we need a 2 over here, and that balances it. All right. Now, still not totally finished with this. This is what's called a formula equation or a balanced chemical equation. We want what's called a molecular equation. So for molecular equation, we have to show the states of matter. So potassium chloride is, and we're going to assume that if we're doing this, we're doing it in water. So potassium chloride, is it soluble or insoluble? Potassium chloride is Big Daddy rule. It's soluble. So it's going to be aqueous, AQ. All right. Lead nitrate. What did we say about all nitrates? All nitrates are soluble. All nitrates are soluble. That's Big Daddy again. So what state will we put there? AQ. All right. Lead chloride. When lead is combined with a halogen, what happens? It's insoluble. That's rule 2. So this one will be a precipitate. So what state of matter will this one end up in? Solid. All right. If it's insoluble, if it's not going to dissolve, it's going to remain a solid. All right. And potassium nitrate. All nitrates are soluble, so this one is AQ. All right. Now, so before I move on from this part, this is where it becomes important because this is the skill that I'm going to expect y'all to be able to do is figure out what's soluble and what's insoluble. So looking at this, does everybody understand why I was saying this was aqueous and why lead chloride is not? Okay, if it's soluble, we're going to write aqueous. If it's insoluble, we're going to write solid. If for some reason you had just Cl2 plus something else, chlorine, diatomic chlorine is always in what state? Gas. All right, H2 is always in a gas. So just be aware of those kind of things when we're doing these. All right, so this is the molecular formula. All right. The next one is what's called a complete ionic. Now, these become very important. Where you see these a lot, especially if you go into people that work at Dow in their solutions department, where they're creating new fuels and things like that, new oils. They're going to deal with this a lot, but really a lot in pharmaceuticals when they're trying to prep a certain drug or a certain thing coming out. And not so much when you're actually doing the work, but when you're doing the coursework to get there. Ionic equations, net ionic and complete ionics come into play. Because you have to know, excuse me, sorry. You have to know what's fine. You have to know what's going to transpire in this reaction and why they're going to do what they're going to do. All right. So if potassium chloride is ionic, if it's aqueous, if it's soluble, what is it going to break down into in solution? Specifically, it's going to break down into its ion. So how would we write potassium as an ion? All right. Potassium is a +1. All right. Chlorine is a -1. All right. Sorry. Yeah, that's okay. All right. Now, so we also have lead nitrate. What is lead's ion going to be in this one? That we said it was aqueous, so we said it was lead 2, so it's going to be +2. All right. This is not difficult. It's just a matter of paying attention to what's there. So nitrate is what? -1. So NO3 -1. All right. Now moving forward, lead chloride is not soluble. So do I split that into ions? No. Anytime we see solid, they stay what they are. So PbCl2 plus potassium nitrate is soluble, so we're going to have K plus 1, and then plus NO3 minus 1. Now, we're not done yet because this ionic equation is not balanced. We have to go back and look at the balance. So how many potassiums did we have? 2. And we're always going to write these numbers in the coefficient place. We're never going to write them as subscripts on this. So we had 2 potassiums. That means we also had 2 chlorines. All right, even though that this is a parentheses, not a 2. All right. Lead, we only have 1 lead, right? And we have 2 NO3s. So I'm going to put a parentheses around this, and then I'm going to put the 2 there just so that I know that I'm going 2 to everything. All right. Lead chloride, we only had 1, so we leave that alone. We had 2 potassiums here. And I can't really fit it on this one, so I'm just going to show it up here that we have 2 of those as well, because we used this 2 to show that. Now, the big thing in the area that you kind of miss things is be careful not to write a subscript of K2 or not to write a subscript of Cl2 or something like that. Make sure you're showing that we have 2 potassium ions with a +1 charge. We have 2 chlorine ions with a +1 charge. Now, we are, hello, congratulations. We are looking for the last thing, which is net ionic. All right, so now complete ionic shows everything in its ions. Net ionic only shows the important elements. So net ionic, and I'm going to change color to write this. That's not even changed color. So net ionics get rid of spectators. All right, so what is a spectator? Okay, something that's just watching, something that's just part of the reaction, or something that's part of it and it's unchanged. So do we see anything that looks the same on the left side as opposed to the right side of the reaction? All right, potassium is a spectator. So we can get rid of potassium. Anything else that stays the same, exactly the same on both sides? Nitrate. So nitrate is a spectator. All right, so your net ionic equation is just what's left over. So what do we have left over? We have 2 chlorine ions plus a lead 2, reacts to form lead chloride. All right. Now, so why is all this important? What does this get used for? One of the things that when you're trying to isolate a certain substance, the easiest way to isolate it is to get it to have two different states of matter, because it's very easy to filter off a water and a solid. So you want to create something like, you want to create lead chloride, which is a insoluble salt, and package that in some way, maybe as a pill or something like that. I don't know what lead chloride is used for. I think it's a component in paint. But one of the ones that you would that you're trying to do, so you're trying to isolate this solid precipitate out to get it to reuse it for something else. You may have interest in the liquid portion for another use later, but for right now, that's the one that would be easy to pull out and separate out and get rid of that lead in this reaction or something like that. So that is molecular, complete ionic, and net ionic. So let's go ahead, and I don't want to overkill these, but let's go ahead and try to do the next one. So go ahead right now, take a moment. I want you to go ahead and try to write the molecular compound for this one. Just molecular compound. All right. So silver nitrate. Since there is not a Roman numeral there, I'm going to assume that this is silver 1. And nitrate is -1 charge, so that means it's going to react 1 to 1. So that's going to be AgNO3. And based on Big Daddy rule, nitrates are always soluble, so we're going to write that that one's aqueous. All right, plus magnesium bromide. Magnesium is a group 2 metal, which we don't really have a rule for group 2 metals, but we do have a rule for halogens, which bromine is a halogen. Magnesium is a +2, bromine is -1, so it becomes MgBr2. And halogens, when combined with anything other than lead, silver, or mercury, are soluble, so this one is going to be aqueous as well. And they react to form this. Basically, the silver and the magnesium trade place, so it reacts to form magnesium nitrate. So it's going to be MgNO3 2. Magnesium nitrate, is it soluble? Yes, nitrates are always soluble, and that's Big Daddy, or the Big Daddy rule. And then we have silver 1 reacting with bromine. So, and it's actually just going to be Br on that one. Because silver, it's silver 1, so it's a silver with a +1 charge reacting with a -1 charge. So now we need to go back and do some balancing here. Yes, and this one's a halogen combined with silver, lead, or mercury is insoluble, so that means that this becomes a solid. All right, finishing up balancing. On this side, we have 2 bromines. On this side, we only have 1. So we need to go ahead, put a coefficient of 2 right there. When we do that, that means that we need 2 silvers. And then we have 2 nitrates now and 2 nitrates, so that's balanced. All right. Now, that's our molecular. Next step is complete ionic. So for complete ionic, what are we going to do to silver nitrate here? Separate it into ions. So silver is going to become a +1. Nitrate is going to become a -1. And I like putting them in parentheses so that I can show that that's a polyatomic ion. You don't have to. It's not incorrect if you don't. I just like doing that to show that it's a group. All right, and then moving forward, magnesium and bromine. Magnesium becomes Mg, what's the charge? +2. And we get that from its location on the periodic table. And then we get bromine -1. Now I'm going to save the coefficients and subscripts until I'm finished. Magnesium nitrate is aqueous, so I'm going to go ahead and separate those. Magnesium +2 plus nitrate -1. And then do I need to do anything to silver bromide? No. So I'm going to go ahead and say 2AgBr because that's solid. All right. Going back to this, we had 2 silver, so I'm going to put my 2 there. We had 2 nitrates, so I'm going to put a 2 there. Can somebody open the door? For magnesium, we only had 1. Bromine, we have 2. So where do I put the 2 for this bromine? Do I put it as a coefficient or a subscript? Coefficient. All right. So that is bromine. Now, magnesium, we only had 1. Nitrate, we have 2. All right. And then everything else is broken down. So now we need to do the net ionic. And so for net ionic, we're just getting rid of the spectators, right? All right, so what are the things, I'm not going to, now just know for you don't really have to scratch them out, but you just do need to recognize what are the things that are only watching. What are the things that stay the same on both sides? So nitrate and magnesium stay the same on both sides. So that's the ones we're getting rid of. So those are spectators. I'm trying to avoid crossing them out just for sake of not doing it. So those are all spectators. So we're left with 2 silvers plus 2 bromines, and it yields 2 AgBr. All right. Any question on this? Yes. Well, the coefficients, the reason why we put those is because they were part of the molecular compound. So we're saying it takes 2 silvers and 2 bromines to react together, and that's what it's going to form. It's 2 molecules of AgBr. Even though they're all the same, we still keep those. Because that's what it's going to take to react. If we just have 1 silver and 1 bromine in there, it's not going to react. It's not going to form that compound. So we know that we need to keep it in a proportion of 2 molecules. All right. So let's look at this one real quick. Go ahead, write the molecular formula for sodium chloride plus lithium sulfate. Yes. Yes. Hmm? Okay, I'll fix it. Just a minute. All right, and the only other thing, sulfate had a charge too. So thank you, Caleb. Look at this one real quick. Sodium chloride plus lithium sulfate, that's going to change to sodium sulfate. So it should be Na2SO4. Thank you. Brain wasn't working. Plus lithium chloride. Right there. No, sorry. All right, lithium chloride, LiCl. All right. So balancing real quick, we need two sodiums, one sulfate, and we need two lithiums here. So that's our molecular. All right. And then sodium chloride, is it soluble or insoluble? That's AQ. Lithium sulfate is soluble, AQ. Sodium sulfate is aqueous, yes, that is soluble. And lithium chloride is aqueous. All right. Now, from an ionic standpoint, we would have Na plus Cl minus 1 plus lithium plus 1 sulfate all right, yields sodium plus 1 sulfate minus 2 plus lithium plus 1 plus chlorine minus 1. All right, going through 2, 2, 1, 2, 2, 2, 2. Yeah, 2 in front of everything except for the sulfates. All right, now, so from if this is in an aqueous solution, if this is dissolved in water, it's just going to separate into the ions. So from the observer's point of view, from observation level, if everything in this is a spectator, because everything is on both sides, will we observe a reaction? No. So for net ionic, basically there is no observable reaction. Because we can't tell that this double displacement reaction has occurred. We can't see it, we don't know it. And if we were to evaporate the water out of it, we can't guarantee which side it's going to end up as. If it's going to end up as sodium chloride and lithium sulfate, or if it's going to end up as sodium sulfate and lithium chloride. We won't know because whenever we evaporate the water, the ionic compounds are going to reform, and we just won't see it. All right. Which that is kind of where I think that's where I'm going to stop today. All right.